Start.
Okay, thank you.
All right, looks like the recorded started. Go ahead, Daniel.
All right. Hello, everyone. My name is Daniel. I'm a software engineer at Intel, and today I'm going to talk about Coredump. Just a very brief introduction and just a demo on how it works. So this is the agenda for today. I'll just give an overview of Coredump in Zephyr. And then this just a brief demo, and then we'll talk about how on like extending Coredump, like writing a new backend and porting to a new architecture and so on. Coredump Zephyr is like it enables us to do like offline debugging for fatal errors. So when for those of you have poked into the kernel code, you may see like a C fatal error call to that kind of thing. So kernel oops, that kind of thing. So inside there, it will call the if the Coredump is enabled, it will call the Coredump routine within those functions, and to you'll go through the fatal handler will call the Coredump front end, and then the front end itself will go through the architecture layer first, so that because the architecture is to dump or output is like the register values, for example, like the instruction pointer, stack pointer, everything that needs that is needed by the debugger to know to figure out like the stack frames, that kind of thing. So so you can start looking at what's going on there. So this one that's the first part from called by the front end to output the architecture related data. And the second part is to actually dump the memory. Currently there's two modes in Zephyr. One mode is just to dump the memory of the thread that causes the exception in the first place. So it minimizes the amount of data that is being dumped. But if this is just what you need, and then also it provides a kind of like a security. Kind of by obscurity, because you're not dumping the whole memory stack. So then the second option, like I said, is like is just dumping the whole memory, where the like just defined by the SRAM, the config SRAM base and the config SRAM size, just it's dumping the whole memory out. So if your say your backend comes to say a flash device, you will need to the flash device need to be able to hold on to that much data. So and for both the architecture data exporter and the memory exporter, they just send the byte stream to the backend, where the backend is actually writing the data to a storage medium. One example is the UART. You just output, you never store it, so you need to capture it externally somehow, or the byte stream, the data can be captured into say, for example, a flash device. After that, if you store in the flash device, it needs to be retrieved somehow. One way you can do it is through the say, for example, the shell module. So next time the system restarts, you can go through the shell and try and retrieve the data. So you can get it this way. So after that, the data retrieval line in the in there is actually divide the online part and the offline part of the whole Coredump process. The left side of the data retrieval line is mostly baked into the application. So the front end and back end is running on the system on the device. So that's how it can dump the data. So on the right side of the data retrieval side is running that part is running on your development machine or the machine that you're trying to debug the application. The first with the data that captured from the Coredump, you will need to send it through some parsers so that it can extract data from your say for example the architecture or target data, because the data is not universal, because the register sets are different between different targets or different architectures. So it has to be a specific parser for the architecture. For now, that's basically it. The other part of the parser is just universal, because it's for memory, which is it's just a byte stream of like just bytes. So that part can be universal, but for the architecture and target part has to be target specific. So the parser will pass all the data and send it to the GDB and use it by the GDB server, so that the debugger can attach to it and start. So you can use like GDB to connect to it, figure out the backtrace, look at data, that kind of thing. So, any question up to this point before we go into the demo? No. Okay. Let's see. Can you see my screen?
Yes, I can, Daniel.
Right, thank you. So on the left side, it's just building the test app, the test subsystem debug Coredump, and this is basically this is basically causing a null pointer exception on the func3, the third function. So it's very simple. It's just this is a test app to make sure that nothing breaks. But this is a sample, for simple samples. We can just use it here to demonstrate how it works. So I'm building and running the app under QEMU x86 and pipe the output to a file, because it's using the UART backend, so we can capture the data there. So you can see there's a bunch of like hexadecimal data on the left side, prefix with pound sign CD colon. So this is the UART output of the Coredump. So with this data, we first need to convert the data into a binary format. This is this is one of the post processing you need to do with the data produced by any backend. If for example, if your backend, like the flash partition backend, is using a particular form, is outputting a particular format, then you need to pass it into just a byte stream. So the GDB server can just get the data and present it to the debugger. So here it's just a simple program, convert the hexadecimal into binary, and then this is the script to instantiate GDB server. Here you can see like using the log file, using the L file, and you can see like the reason for exception, like pointers. This is just I'm just enabled the verbals display, so so you can see what's going on. So I'm just and then just using the host GDB because it's easier. I don't have to go through all the whole path to the SDK. But let's just connect to the GDB server. Let's present on the left side. You can see like it tells you where is like where the fatal error occurs. So if you do like look at the backtrace, you can see the like it's this is where the line 14 is where it's like it's like stopping there. So this just a brief demo is how it's basically how it's nothing fancy. Just you well when the fatal error comes, you just grab the data, post-process it somehow if needed, and then you just feed the data to the GDB server script, and then and you can use it in say GDB. So let's go back to the slides.
Daniel, there's a question in the chat.
Okay. Yeah, the question is that when you read the UART output, how can you be sure if the Coredump is complete? Is there a way to check if a line has been dropped? What will happen if some errors sneak into Coredump messages? At this point, there's actually no error tracking. Wait. Let me share. Wait. You can like let me go back to the data. The UART is the UART output itself would do like for example here a begin and end. So this is how it marked the beginning of the Coredump and the end of the Coredump, and if each line is like for example like it prefixed with a pound sign CD colon, that's one line of data, and the UART backend itself assumes that if you send one line, it will print that line and nothing gets in between. So but sometimes if your system is set up in a way so that the UART can output something in like from anywhere, so like the lines can be like intertwined together, then this backend would not work. But but if you are using the say for example the logging subsystem to get the data out, it should be okay, because the logging subsystem will make sure that each line outputs by themselves. Does that answer your question? There's another question. There's like is this the GDB process the same in spite of the architecture? For instance, the device was a Cortex AMS. I'm not sure what you're asking. So you asked about the GDB server or the GDB debugger. If it's the server, then there's a parser to output there's a parser to grab to parse the architecture data, the target data that is being output by the Coredump module, and it is not exactly architecture wise, because like it's like a byte stream. So the parser the whole GDB server doesn't really care, but the parser themselves does. It's like the parser needs to know architecture, the format of the architecture stream, and but from the debugging side, because you're feeding it the L file, so it does know what kind of architecture is being this, it knows what the target architecture is and know what kind of things like what kind of like register file that it needs to read. And then there's another question: what did you? How do you configure to get the Coredump at all this?
That was answered down below in the chat with config debug Coredump.
Yeah, I was just going through.
Daniel, are you trying to share something?
Not yet. I was trying to get back to the to the slides.
Okay, you're not sharing anything, so just
yeah, I was just trying to get back to the slide and. It's uploading. Just a sec.
Okay, we got the slides up now.
Yeah, because when I try to share the screen, the slide goes away, so I have to go back and forth. So yeah, that's basically the demo itself, and then there's a questions on say how does it handle multiple threads if more than one thread had an error, how would the situation get handled? At this point, there's actually nothing about multi-threading, like even multi-processing this, because like at the point where the error occurs, it will dump everything. So there's in terms of thread context, there's only one thread. When the error occurs, there's only this running inside some thread context. So it will dump that particular thread context. But if you want to look at other threads and things, you will probably set the memory exporter to dump all the memory, so you can look at like the what kind of like a thread objects you have, and then the thread IDs, and go and then look at using the thread ID to refer to the actual thread structure, that kind of thing. So that's basically it. There's none. At this point, the Coredump is kind of primitive at this point. It's just dump everything. So yeah, at currently, like the only the x86 and the ARM Cortex M are supported. And there's only two backends. One is UART that you've seen through the demo, and then there's another UART that's it's just dump the data into the flash partition. It's like a sample backend. It has a shell integration where where after you boot the device, you can see if there's actually Coredump data in the flash partition, and you can verify if everything is there, because the backend has some type of checksum there to make sure that everything is not corrupted. And also the dash shell module can dump the flash dump the Coredump data, so you can grab the data and fit it back into the GDB server script, and then you can start debugging. So if you want to extend the backend, this is like it's more or less very simple, because the front end and all the exporter just give the backend a byte stream. You can store it any way you want. For example, if you want to do it to a flash, not just flash precision, but a flash where you need to take care of like erasing the block and everything. Then you can have a buffer, just take in enough data to write to one block and then erase the blocks, right? So the backend is supposed to be very simple. Just take a byte stream, write it, and then if you need, you can grab the buyback and like on the flash backend, using the shell module to retrieve the data. There's a question asking if there's any matrix on the RAM flash size needed to enable Coredump. I actually have not went through the RAM report or the ROM report on this, but it's highly dependent on the architecture itself, because it will require code to dump the register file, which means like that size might change a little bit, but another thing you have to be aware is that how much storage space you need for the for actually dumping the data. Like if you need to dump the whole memory, you need to be able to have say a flash partition or external storage device that can store the whole thing. And or in addition to the memory data, you need a little bit more for the to store the register file, the dump of the register file also. This go back to the slides. Like this is just the extending the backend is simple on this. But when you try to extend the Coredump to a new architecture and target, is a little bit more complex, because you need to know what you need to define. Actually, you need to define your own data structure on how to how the register files is going to look, because you need to write a Python parser to parse the data, and that parser needs to be able to present a GDB register package to the GDB server, so it can be sent to the debugger. So that's so it's the extending architecture is more involved. It's two parts: the online part where you dump the register file, and then the offline part where the parser, you need to pass the register file with the dump of the register file and present it as a GDB register package to the debugger. So I think we have only like 5 minutes left, and so any more questions?
Are there other architectures that you're targeting to add this to in the near future?
Not at this point. It's yeah. I have to be honest. I'm not dealing with much of the architecture side of stuff. So, but I try to make this as easy to extend as possible. So if you're trying to extend an architecture and it's too annoying to you, I welcome any feedback, so I can make it easier for people to extend Coredump in the future.
Is there any other way to record the state of the device in case of fault? So, for example, when we have a debugger connected in the CI and something breaks, can we dump the state of the device that way?
Oh, let me try to understand. So you already have a debugger attached to the system, and you want to dump the data, right?
Right. Yes.
No, actually, if you already have a debugger, you can stop anything. But the Coredump module doesn't work this way. So it's only it's only called by the Zephyr kernel fiddle handler. So only if there's a fatal error, then it will go through the path to dump all the data.
Okay. Thank you.
Any more questions for Daniel? All right. Well, thanks a lot, Daniel. I'm going to go ahead and stop the recording.
Thank you, everyone.